Welcome to tutorial on analog electronics, and in this tutorial we'll be basically today discussing about the Zener diode. Okay, so the Zener diode basically falls into a class of, falls within a class of, breakdown devices, or rather devices that operate in the breakdown region. Okay, so let's just bring up a graph over here which would make things easier for you all to understand. Okay, so there it is. So in this graph, as you can see, this basically is the characteristics. It just basically represents the characteristics of a PN junction diode. Okay, so you can see that it's basically has two parts, one on the right and on the left. So the part on the right represents the forward characteristics of a PN junction diode. Okay, and now the left one represents the reverse characteristics. So we can see here whenever the PN junction, whenever a PN junction diode is basically reverse biased down to the breakdown voltage right over here with the red mark. Okay, so whenever the reverse voltage across a PN junction diode is equal to the breakdown voltage, okay, then we shall see a sudden surge of current through the reverse biased PN junction. Okay, so we discussed its cause back in the previous tutorials where we had discussed breakdown phenomena. Okay, so now Zener diode, okay, is basically a special type of diode that's been designed in order to operate in the breakdown region. So this part, as you can see in this case where the breakdown occurs, okay, after the breakdown voltage is reached, this part is known as the breakdown region. Okay, so there you go. So now the Zener diode today, which we're going to discuss, operates basically in the breakdown region, and that means this particular device is used in the reverse biased state. Okay, so with that kept in mind, I'll show you the circuit symbol. Okay, so there you go. In case of the circuit symbol, okay, we have the circuit symbol basically looking something like this. So there is a short Z type of structure. Sorry, there it's a bit crooked over there. Okay, so that's better. Yeah, so that is basically how a Zener diode would basically look like. So here we have the cathode of the Zener diode right over here. Okay, and this one's the anode. Okay, this terminal. So we can see here that the Zener diode, okay, is not all that different from a simple PN junction diode. It has a cathode and anode as well, but its cathode is being modified with a Z type of shape, since its name begins with Zener. So this is basically done in order to show that it's basically a Zener diode. Okay, so that's the circuit symbol over here. So having that said, we can say that since the Zener breakdown, since the Zener diode over here is basically a special type of diode designed in order to operate in the breakdown region, okay, it has a certain power dissipation capability that it's just denoted by PZM. So that's the maximum Zener power dissipation capability, and also it has a certain value of breakdown voltage. Okay, so this breakdown voltage is basically represented by VZ. Okay, so now for every Zener diode there is a particular value of breakdown voltage and a corresponding maximum power dissipation capability. So whenever the Zener diode operates in the breakdown region, it gets hot due to conduction of sufficient amount of electric current through its reverse biased PN junction. Okay, so now whenever we take a look at this reverse reverse characteristics over here, we see that in the breakdown region, the breakdown voltage almost remains fixed at this point, and the current can increase no matter what. It can just increase sufficiently, but the breakdown voltage doesn't suffer any sort of change. Well, with this property, okay, we can just use a Zener diode as a voltage regulator. Okay, I'll show you how. So here, if you all would just focus your attention towards the circuit over here, which I'm just trying to draw over here. Okay, so there you go. We have a So let's say that we have a resistance over here, which is our load resistance. We just call it RL. All right, and there is a particular voltage source. Okay, there you go. That's the voltage source over here. Let's say we have a voltage source of about, let's say, 16 volts. Okay, no problem. Now we require that the voltage across this load resistance be kept, okay, constant. Alright, so now this could be achieved by a Zener diode. Okay, if we just connect that in parallel with the load resistance, basically. Alright, now if we just go back to what we discussed previously, okay, so we saw from the characteristic that the current can increase no matter what, but the breakdown voltage remains almost constant at its particular point over here. So you can see that whenever the breakdown voltage is reached, okay, the amount of current that should flow through the Zener diode could be, increasingly large, but still the breakdown voltage remains constant at its particular point. So due to this property, as I said, we could basically utilize the Zener diode in order to maintain, okay, voltage is constant up to from fluctuations from the currents flowing in a circuit. So it doesn't matter whether the current would increase or decrease. Once the Zener diode is being operated in the breakdown region, it always keeps the voltage constant. Okay, so let's say we have this Zener diode. As I said, let's say our Zener diode has a maximum power dissipation capability of, let's say, 30 milliwatts. It's quite small, but still, as an example, we can just take it. And let's say it has a breakdown voltage of about, let's say, 10 volts. No problem. So here we need to make sure that the Zener diode, of course, as like other devices, like all devices, every particular device has a maximum, handling capacity. So the maximum amount of current that should flow through this Zener diode, okay, once it's being used in the circuit, okay, without damaging it, could be calculated if we would just make this simple calculation over here. So we could do that by just calculating it this way. So the maximum current, that's IZM, flowing through the Zener diode, okay, would be given by PZM divided by the breakdown voltage. Okay, so there you go. If we have 30 milliwatts, okay, so 30 into 10 to the power minus 3 divided by, that's 10. So with this way we'll just get something about 3 milliamps. That's quite small. So we have this Zener diode, okay, with a maximum current handling capacity. Okay, I'll just use blue in this case, with a maximum current handling capacity of 3 milliamps. Okay, so there you go. So we're basically having here a Zener diode that can handle, a really small amount of current. Okay, so but still then it can basically serve as a voltage regulator. So we shall use this in our circuit. Okay, no problems. So now keeping this in mind that it can handle up to only 3 milliamps, we need to connect a series resistance which will basically prevent the current flowing through the Zener diode from rising. So there we go. We connected a resistance right over here. So that's basically our circuit which we would basically study in this tutorial. So now in this case, as you can see, that our Zener diode, okay, can tolerate at a maximum of, let's say, 3 milliamps. So whenever, let's say, we connected it this way, okay, once the voltage about these 2 points, that's A and B right here, okay, I'll use red in this case. So whenever the voltage across these 2 points, that's A and B marked in red, okay, whenever they would be, voltage across these points, let's say I call it VAB, whenever this voltage is about greater than or equal to the breakdown voltage, that's 10 volts, okay, the Zener diode would basically operate in the breakdown region. Okay, so this is basically VAB needs to be greater than or equal to the Zener breakdown voltage, which is 10 volts in this case. So if we just imagine this circuit, okay, if we would just imagine this circuit as, let's say, 16 volts, okay, connected without the Zener diodes, then we would have something like this. Okay, here would be RS and this would be, let's say, the load resistance. So we need to ensure that the voltage at these points is of course higher than the higher than the Zener breakdown voltage in this case. But in this case, in order to determine the voltage that would basically exist here, that's VAB, we would need both the values of the series resistance as well as the load resistance. Okay, so let's say the load resistance in this case, let it be about 3k ohms. Let's say we want to drive a load, or rather keep the voltage across voltage constant across a load of 3 kilo ohms. But the series resistance needs to be calculated upon the Zener diodes parameters, so we cannot just assume it. So in that case, we needed to calculate the maximum amount of current through the Zener diode, which we did. But now, since let's assume in that case that our Zener diode is operating in the breakdown voltage. Let's just assume that. So whenever our Zener diode would operate in the breakdown voltage, as I said, or rather as seen from the graph over here, that the voltage across the Zener diode would be fairly constant no matter how no matter how much the current would increase. So in that case, we have the Zener breakdown voltage at 10 volts. So that means that the voltage across the Zener diode would remain constant, or rather fixed, at 10 volts. So we just assume the voltage across VAB that's equal to 10 volts. So whenever that would happen, or rather that would basically take place, so we can basically calculate the amount of current that should enter through the load resistance, that's IL. So here we can just calculate IL, something over here. Okay, so here IL would be something like, it'll be 10 volts, okay, divided by 3 kilo ohms. Okay, so that basically gives us a load current of about, let's say, 3.33 milliamps approximately. So we are having a load current of approximately equals to 3.33 milliamps if the Zener diode is actually operating in the breakdown region through the load resistance over here. And now we knew that the maximum amount of current, that's the IZ, or rather the Zener current, okay, denoted by IZM, that would be something about 3 milliamps. Okay, so the total amount of current that should flow through both these arms, one through the load resistance and through the Zener diode over here, would be equal to, that's I equals to IL plus IZ. Okay, so here I would represent the total amount of current coming from the supply voltage source. Okay, so that would be something like 6.33 milliamps, or rather I'll just break it up. Okay, no problem. So IL would be 3.33 plus this is 3 milliamps, so we're getting 6.33 milliamps over here. No problem. So that's basically what the total amount of current should be. Okay, so now if this total amount of current coming from the supply source is about 6.33 milliamps, then the voltage across the load, across the series resistance right over here should be about 6 volts, since we have already 10 volts from the supply source dropping across the Zener diode, since it is in the, or rather since it's basically operating in the breakdown region. So the rest of the 6 volts would occur across the series resistance. So we'd have 6 volts dropping across the series resistance. So here in this case, the current that should flow through the here we have the current that should be actually flowing through the series resistance as well, and we know the voltage across the series resistance as 6 volts. So we can basically calculate the value of the series resistance as something like this. That's RS, okay, equals to 6 divided by, that's the voltage across this series resistance over there, divided by the total amount of current, that's 6.33 milliamps. Okay, that's 10 to the power minus 3 amps. Okay, so it's basically comes down to something like 947 ohms. Okay, so there you go. So 947 ohms, this is quite an odd value and not industrially available. Okay, so in that case, if we would just take it approximately equal to 1k, or rather 1 kilo ohms, and use it as the series resistance right over here. Let's say we take it as 1 kilo ohms, no problem. So in that case, the series resistance would hold a value of approximately 1 kilo ohms in this case, and with that value we need to ensure that the voltage across the terminals A and B be greater than or equals to 10 volts. So if we calculate again, okay, assuming the series resistance as 1 kilo ohms, then we're getting something like this. So we have the VAB, or rather the voltage across the terminals A and B, would be given by the supply voltage, okay, so that's basically 16 volts multiplied by, okay, the load resistance, that's 3 k ohms, okay, and divided by the total of the total resistance right over here, that's the RL plus the series resistance, okay, that's 3 plus 1, which makes 4. So that's 4k down here. So we're basically having something like this, that's 16 multiplied by 3 divided by 4. So that gives us about 12 volts, okay. So therefore we're having the voltage across the terminals A and B approximately equals to 12 volts in this case. So which means that if we initially maintain a voltage across the terminals A and B at 12 volts, then obviously the Zener diode would eventually operate in the breakdown region. So this way, if we just construct this circuit, okay, putting it finally as something like this, okay, so there's our Zener diode, okay, no problem, and here is our load resistance of 3 kilo ohms and our series resistance of 1 kilo ohms, and we have a supply voltage source of 16 volts, no problem. So if it's that way, if in this way we make the arrangement, then our circuit right over here would give us approximately a voltage, or rather a fixed voltage of about 10 volts across the load resistance right over here. So having said that, we basically conclude our session of discussion on the basic construction of a regulated power supply with Zener diode, or rather basically constructing a Zener diode as a voltage regulator in a particular application, and the Zener diodes as well. So hope you've enjoyed this tutorial, and don't forget to catch us next on our forthcoming tutorial. So till then, it's just a goodbye for now, and thanks for watching.